Hi everyone, I'm Riccardo Russo, a master student at the Aalborg University in Copenhagen, and this presentation will be on building finite difference schemes physical models in Faust. To do that, we will be using the FDS library, which is the result of a work I've done at Graham in the previous month, with the goal of introducing finite difference scheme synthesis into the Faust programming language. This is the agenda for today. This workshop will be divided into two main parts. In the first part, I will introduce some of the FDS theory. Some of you may be already familiar with this, for others it will be completely new. This part is mainly oriented towards those who are new to FDS and is intended to give you some of the mathematical basis that will be useful throughout this tutorial. Then I will move to the hands-on section. First, we will implement the first FDS model without using the library. This to understand the basic principles of finite difference schemes in Faust. Then we will have a brief look to the cellular automata approach, which is used inside the library, and later we will build all the schemes we obtained on paper in the first part by using the library. Lastly, we will take a brief look at the interaction models. So first, what is a finite difference scheme? It's a discrete model that simulates a continuous system. It's a method which is largely used in engineering for system simulation, and it's actually a pretty old idea. Basically, it consists in numerically approximating a continuous system, usually a system of partial differential equations, with a discrete space-time grid, like the one that we can see here in this image, where we discretized the time and space axis, obtaining a series of discrete points. So why FDS? What are the advantages and disadvantages with respect to other physical modeling techniques? Well, directly simulating a mathematical model allows to not make any assumptions on the mathematical solution. So this makes this method very generalizable and flexible, and also very accurate. So, for example, it's easily applicable to nonlinear systems. On the other hand, though, it's really computationally expensive. At the moment, the guys from the Stefan Matlab group are working on state-of-the-art physical models, which can produce realistic sounds, but also which require less and less computational power. Here are a couple of examples. This was a trombone, and here's So, as you can see, this method allows to model all the tiny details that make a sound realistic. So, first, let's start from the basis. The starting point for finite difference schemes is that musical acoustic systems are defined by partial differential equations, PDEs, which are accompanied by regions of definition, boundary conditions, and forcing terms. The state of this system depends on the time instant and the spatial coordinates. It can be defined as a function u, which depends on x and t. So the first steps for defining a finite difference scheme physical model are first to formulate the mathematical model. Then we need to define the space and time sampling steps. And once we obtain those, we can discretize the partial differential operators to obtain an update equation. Lastly, we need to implement the boundary conditions. So first, let me do a parenthesis on the notation that we will be using. This is the same as it's used by Stefan Matlab in his book Numerical Sound Synthesis. And it's basically just a way for writing partial derivatives. So here, instead of having this expanded notation, which is most commonly used, we can just write it with a subscript variable, which indicates the variable in which we're going to derive. And this is, for example, first order, second order, and mixed derivative. This is just a notation, basically. So let's get into the real stuff and build our first finite difference scheme mathematical model. So the first thing we need to do is to define a mathematical model. And the simplest possible equation in acoustics is the 1D wave equation. This is a second order partial differential equation in time and space with solution u, which depends on time and space. A partial differential equation, well, a differential equation is basically an equation in which the unknown is not a variable, but it's a function. And so in this case, our function is this u. And u represents the state of the system at time t and position x. And the state is, for example, the vertical displacement of a vibrating string, or the pressure value inside the tube, or things like this. C is the speed of sound in the medium, and the medium is the material of which the system is made. So, for example, for a string is metal, for a tube it's air. T is defined over a positive real domain, because of course time can't be negative. And x is usually bounded over a finite length L, which is the length of the string, the length of the tube, or in general of our object. And we can calculate the fundamental frequency of vibration using this relation here. So we have our mathematical model, and we said that the second step is to obtain the sampling grid. And to do that, we need to first define two sampling steps, k and h, for time and space. These are just two numbers that define the space between the sampling points. So then we can move on the grid with the two integer indexes n and l. And so what we obtain once we discretize our system and we simulate it, what we obtain is a discrete u of ln, which approximates the continuous solution to the system that we saw before. And this discrete function will be made of n equals L over h data points, because of course the number of points will depend on the sampling grid. So if our L is 1 meter, for example, a 1 meter long string, then we will obtain a number of points which depends on 1 meter over the sampling step. So we need to be aware that the two sampling steps are not independent, and they're actually bounded by a stability condition. In general, finite difference schemes physical models are tend to be unstable, and when they are unstable, they blow up. So the signal goes to infinity, and what you hear is just a really weird noise from your headphones. So to be sure that our system will be stable, we need to impose this condition, and so we cannot choose these two steps independently. And this is the Courant-Friedrichs-Levy condition, CFL. So we have our mathematical model, we have defined our sampling steps, and now we can go on and discretize the partial differential operators, which is actually the core of finite difference schemes. Here we have the difference operators in time and space in different versions, and what you need to know is that the centered one is more accurate. This looks like a lot of math, I know, but actually these are just basic algebraic operations. These can then be combined to obtain higher order derivatives. Okay, so we have everything we need, and then we can now discretize the mathematical model. So we started with this equation, which is in the continuous. Then we can apply the difference operators. I will try to show most of the steps to make it more clear for you. So we can then expand these as we saw in the previous slide, and this is what we obtain. Then we need to solve for u of n plus 1, which is our unknown, because of course it's the next step for every single data point, and it's what we are looking for. So if we solve for these, this is what we obtain, which is an explicit recursion relation that can be directly solved numerically. So here you can see a graphical example of the time and space dependency for the relation we obtained in the last slide. Basically, to get the state of our unknown, UL of n plus 1, what we need is the current state of the point L, the current state of the two neighbors, L minus 1 and L plus 1, and the past state of L. So you might have asked yourself, how do I know the current and previous steps? How do I get them? Well, we decide them. So this is called setting the initial conditions, and well, to make things more simple, we can set everything at 0. So what we do is, when we start the simulations, we first set all the data points for the current and previous time steps to 0. So we have our initial starting states. And also, what do we do at boundaries? When we get to the boundary of to the endpoints, for example, of our string, we would need the next point to calculate the next state of this point, but we don't have them. And there are many things we can do. This is called setting the boundary conditions. The most simple and used boundary conditions are these two, the Dirichlet and Neumann conditions. In the Dirichlet condition, what we do is simply we consider the next point, the virtual point, to be 0. This is, for example, the case of a string, where the next point, well, the two endpoints are fixed and they can't move. The Neumann condition, on the other hand, involves solving a little derivative like this. And it can be considered as a free end. So we have our point that it's free to move. For example, it's free at string, which is free to move on one side. In the case of a tube, things are the other way around. It's pretty weird, but it's you can consider that if tube has an open end, the pressure in that point is 0. So because it's the pressure of the atmospheric pressure. So you can see it this way. So now let's go on and try to implement a Neumann condition in the point L equals 0. We need to solve this little derivative, and if we do that, expanding this operator, this is what we obtain. So then we can apply this to the update equation that we had before, and this is what we obtain. So this is the update equation to be used only when we want to calculate the next state of the point L equals 0. Okay, so we did it. We got the algorithm for our first finite difference schemes physical model. As you will see though, the sound is pretty boring, and especially in Faust, since it's real time, it will ring forever. We can fix this by adding a damping term. Every instrument in the real world experiences damping, which is the cause of the outcoming sound to fade out. And we can describe this in math with a term which depends on the velocity, or the first derivative. And here sigma 0 is called the damping coefficient. It's a number which depends on the physical characteristics of the object. We can go on and discretize the damped wave equation as we did before for the 1D wave equation. We apply the operators, the difference operators, and we can then expand them. Now we will skip some math here, but you're very welcome to try and see if you obtain the same result. This is what we obtained, and this is the update relation for the damped wave equation. This update equation has the same space-time dependency and stability condition of the one we saw before, but as we will see, it sounds a bit better. So, before moving to the hands-on section of this tutorial, I would like to introduce you a bit to how these algorithms are usually implemented. In imperative programming languages, we can use arrays. So we allocate 3 arrays for the states, for the time states n-1 and n+1, each one with a number of data points equal to the total number of spatial grid points given by L over H. So we have, for example, our 1 meter long string, and we will have a number of data points, which of course depends on the spatial sampling step H. Then we allocate 3 arrays, each one with that number of data points. And we cycle between them, updating the states at audio rate. We can then obtain sound by reading the current state of a single data point in one of the arrays. So this code snippet shows how the 1D wave equation is usually calculated in Matlab. The first cycle, this one, is on the time samples, like an audio process callback, for example. And this cycle is the loops between all the spatial points. So this is exactly the update equation we obtained before. And we cycle over all the L data points with to a maximum of n, which is the maximum number of spatial data points. Then we read the samples at out position, which is one of the data points. And then we update the states. In Faust, we don't have arrays, so we have to find a completely different way of doing this, as we will see in the next section of this tutorial. Okay, so now it's time to get our hands dirty and implement all the algorithms that we obtained on paper in the last part of the tutorial. I will try to do everything with the online compiler, which you can reach at this address, faustide.gram.fr, so everyone can follow with any operating system. So the first thing we need to do is we need to understand how to build a finite difference scheme in Faust without using arrays. So let's start with the simplest one, the 1D wave equation, and just to be so we are on the same page, this is what I'm talking about. This was the first scheme we obtained in the last part of the tutorial, and it's the simplest equation, the simplest possible equation in acoustics. So I'm gonna write the equation here so you can see it. So this is the equation that we want to calculate. So the first thing we want to do is we want to set our sampling steps. In audio, what we do is to set the time step first, contrary to what is done usually in other engineering applications, as this depends on the system sampling rate. So we can now set k equals 1 over ma.sr. Here I'm using the ma.sr function, which returns the system sampling rate. Now, we saw that we can't choose the two steps independently, but we have to, let me write this, lambda needs to be minor or equal to 1. So, this also means that h needs to be greater or equal to c times k. So first, what we have to do is we need to set the speed of sound in the medium, and we will set it as 344 meters per second. And this is just the speed of sound in the air. So now we are ready to set the space sampling step. We will set lambda equals 1, as this is the most stable condition that we can have. So we are as near as possible to the stability condition. So we can say that h equals c times k. And then let me write this for simplicity. We have that lambda equals c times k over h. Okay, so now we want to actually code the update equation. What we can do is to start by coding a function which does the calculations we want. So it takes the present state of itself and the neighbors, which we will call west and east instead of these, which is a bit more complicated to write. And the past state of itself and outputs the next state. So to do this, we can write update EQ. We'll take in input U west, U, and U east. So current state and two neighbors equals, and this will actually do this. Let me just copy paste for simplicity. So 2 times 1 minus lambda squared times U minus U delayed. This is the delay operator in Faust. Basically, this means one sample delay. Then plus lambda squared times U west plus U east. Okay, this can work, and this will calculate our update equation. However, if we want to get sound, we need to interact with our scheme, our mesh. So let's add a forcing term to do this. We can add f in, and we will have to also get this from outside the equation. So I'm gonna put this first. Okay, great. So we have our equation that will calculate the state, but as you might remember, this is valid only for one data point. So what we can do is we can place many of these functions in parallel with the Faust par iteration, obtaining our mesh structure, our scheme structure. So first, let's define the number of points that we will want. Let's choose something simple. So now we can define our structure. So as I said, we can use the par operation. Let's build a function called build 1D scheme. This will depend on the number of points. This equals to par e points and update EQ. And we can already try to run this to see what we get. So let's write process equals build 1D scheme and points. Let's try. And this is what we obtain. As you can see, we placed 3 of these blocks here in parallel. And what these represent, you can see this as 3 elements inside an array. So each element in the array will perform the update equation operation. But of course, this will not work at all because we need to fill the neighbor points. And when I say neighbor points, what I mean is that this point here, for example, will take the forcing component, the west neighbor state itself, and the east neighbor state. So he will need a term from the outside, the forcing term from the outside, but also the states from this point and this point. So to get these states, we can create a feedback loop. Let me call a function called, let me create a function called model. This will also take in input the number of points. And then we can call build 1D scheme points, then here and bus points. and then we call process equals to model and points. So here what we did is we declared a feedback loop using the tilde operator, and bus is simply a way to call number of signals in parallel. So here we are requiring that what comes out from this goes in a feedback loop inside a bus with 3 signals. So let's try and run this. And okay, so this is what we get. And as you can see, this is more clear now. We created a feedback loop with so since we have 3 points, he created 3 feedback loops with this bus function. Now, the problem, as you can see, is that we need to bring the signals into their correct places. Now they're just going into the first empty spots they find. And to do this, we can use the root primitive. This function works by taking the signals and defining routing with numbers. We will have 3 state signal inputs and 3 force inputs, so 6 inputs. In output, we will have 3 states plus 1 force for each equation block. So 4 times 3 equals 12. Let me delete this process because we won't need it anymore. So as I was saying, we have let me call a function called routing points equals root. So in the root primitive, we first need to define the number of inputs and the number of outputs. So I said it's 6, which again it's 3 state signal inputs, 1 for each point, and 3 force inputs, 1 for each point. And then we will have in output 3 states plus 1 force signal for each equation block, so it's 12. So now things are going to get a little bit complicated, so let me write everything and then I will explain later. Okay, so I created my routing, and what I did is I modified the this version here, which I had before, which I'm gonna delete, and I added before our scheme, I added my routing. So this is gonna take the signals that are fed back from this bus, and this function is gonna take care to route each signal where it has to go. So let me delete this line here, and then let me call the process model and points. Let's run this, and again, this is what we obtain. So this is what the routing does. So if you look at these numbers, what I did was this. So I took the first signal in input, so 1, and routed it to the third output here, 1, 2, 3, because the root primitive is 1 indexed, and we'll see why. And then also the first input, I routed it to the 6th output, 1, 2, 3, 4, 5, 6, and the same for each other signal. So I took the second input and routed to the 4th, the 7th, and 10th output, and these for each signal. Then I took these, which are the 4th, the 5th, and the 6th input, and routed. These are the forcing signals, and routed to the first input for each equation block. As you can see, here there are here we have two connections where there is a 0. Root is one indexed before, because if I place a 0, this means send a 0 signal, so a null signal, and this is what I do at the boundaries. So here and here, what I'm doing is I'm implementing a Dirichlet boundary condition. So I'm assuming that the neighbor that should be here and here is fixed. So it always sends a 0 position signal. Okay, so we have our working model, but however we cannot get any sound from it because we need to need something to interact with our mesh. First, well, as a force model, we can simply, for now, we can simply create a button, which I'll call play equals button, and we will send this through an impulsify function, which will turn the button signal to an impulse. Then we need to choose which point we want to send the force to. Of course, we can excite each point at the same time, but it's not really realistic, right? It's like I have a string and I pluck it in every single point at the same time. It's not really physical. So yeah, let's create. Let's start by creating two sliders. And then we want to code some functions to, well, to send this signal to the right, into the right place. So point selector in will get the number of points and the point we want, and we can use the select out n function, and this will get the same inputs. And also we want point selector out, same inputs, and we can use the select n. So this function takes one input and outputs n signals, where each one is 0 except the one selected on I. So this is perfect for the input signal, whereas the select n function takes this number of signals, and what it does is it outputs only one of the signals it gets in input. And sorry, I made a mistake here. This is points, because this is the number of points, this is the point we want. Okay, so now let's try this out. We can call our process. Now we have the force signal and we route that into the point selector in function, which we will take and then this will go will be plugged into our model function, which is this one, and takes n points, and then this will go through point selector out, n points, out point. Okay, so let's try this out. And well, of course, now he's complaining because I have another process defined here. Let me take this out and rerun this. Okay, so it works. as you can see, this was pretty annoying, and the problem is that the number of points is so tiny that the outcoming sound is super high. But yeah, we achieved it. We built our first finite difference scheme in Faust. However, well, if you think about it, it was a huge pain. And if any of you had any experience in coding finite difference schemes in Matlab, for example, in this moment you might be thinking, okay, but in Matlab this is way more easier. And you're right. You're actually right. So we can, let's say, we can use a different approach. If you look at the update equation, you will see that this is linear. So what we're doing is we're simply applying some coefficients to each neighbor signal. So this is the first coefficient, and it's applied to the current state of the point. -1 is applied to the past state, and lambda squared is applied to the two neighbor signals. So, and let me show you something here. Since the derivatives are mirrored, we can define a neighborhood with a radius. So, basically, for example, in this case, we could define our neighborhood radius as 1, because we need 1 point on the left and 1 point on the right. Also, we need to define a time coefficient which indicates how many times back on time we want to go. And in this case, it would be 1 again, because we just want n-1. And this approach is similar to what is done in a family of algorithms, actually, called cellular automata. And this is exactly the approach which is used inside the FDS library. So let's try and build the same, well, almost the same algorithm, but by using the library. Now, instead of writing a function to perform the equation as we did before, I will go on and just define the coefficients that are going to be applied to each of the various states. So we have, let's say, A equals 2 times 1 minus lambda squared. We have B equals lambda squared, and C equals -1. And these are exactly the coefficients that we can see here. This is pretty clear, I hope. Then we want to define the neighborhood radius and the time coefficients. So we said that they are going to be R equals 1 and T equals 1. So what we want to do now is to create a coefficient matrix. So we want to arrange the coefficients so that they make sense for the algorithm. So A will be applied to the current state of the point, B to its neighbors, and C to the past states. So for the time instant n, we can call mid-coef equals BAP. And for time instant n-1, we only have the current point, so L n-1. We don't have, for example, L plus 1 n-1 or L minus 1 n-1. So we can apply 0 where we don't want to get the signal. So mid-coef del equals 0, C 0. No, sorry, 0. I hope this makes sense. If I go back on the scheme, what I'm doing here, this would be mid-coef. So this part here is A, this here is B, and it's gonna go to the neighbors, and this one is C, and we don't want the neighbors passed signals, so here's why there is a 0 here. So we already implemented the 1D wave equation, so let's make things a bit more complicated and let's implement different boundary condition for the left point. So what we want is to implement the Neumann condition, which is this one, the one we saw before. And let me write the equation for the Neumann condition. So now we want to define another coefficient, which is going to be d equals 2 times lambda squared, and the corresponding matrix, which is going to be left coef equals 0 a d. This is the left boundary, so we physically don't have another point to get the signal from, so well, the coefficient is gonna just be 0. A, it's the same as you can see here, and here we have d, which is 2 times lambda squared. And for the past state we still have c, so we don't have to define anything else. So now we want to decide what the coefficient scheme will be. So we want to set the coefficients for each point in the mesh. So first we want to set number of points again, and it's gonna still be 3. Then defining the scheme is very simple. We can simply use a part iteration, since each point will have the same coefficients matrices except for the left one, and we will put the left one first because, well, it's left. So let's call our scheme equals left coef mid coef del, again because for the delayed version we don't have another coefficient for the left point, and then we can use the par iteration. So it's gonna be e minus 1. It's gonna be points minus 1 because, well, we already defined 1 point, the coefficients for 1 point, and then mid coef del. Okay, so now the hard part is done, and we can now simply call one library function from the FDS library to obtain our working model. So let's call process equals fd.model1d, because we are in 1 dimension, and points. This will take in input the number of points, the radius, the time coefficient, and the scheme. So points, and well, let's try and run this. And as you can see, it is a bit different, but this is exactly the same model that we obtained before, except, and if you check here, this is the same routing that we had in the previous model, except that now each point takes in input also the scheme coefficients. As before, if we want to interact with the mesh, we need to put some other functions. And now, however, we might want also to get the signal or to excite our mesh in between 2 points. And to do that, we can use the interpolation functions that you can find inside the library. So instead of getting these, we can try and do something else. So we can call our new process function play, This time I'm gonna need to spread this signal, and then we can call fd.interp1d and points, and this takes, as before, it takes in input the number of points and the point that we want. Then we can call fd.1d and yeah, again takes number of points, r, t, and the scheme. Well, then we can call also fd.interp1d out, which is just the it's the version of this function just to get one signal, basically. So and points out point, and let's try and run this. Okay, so this works, and it's just as annoying as it was before. But I hope you agree that this was easier than the approach we used before. Now the cool thing is that while before we had to change the routing for example, if we wanted to change the number of points or change the type of a scheme, we had to rewrite the routing each time manually, and that's very annoying. But in this case, we can simply, for example, change the number of points. And also, yes, another thing, since we are linearly interpolating, we can change the step to be a float, and so we can get the signal in between 2 points. And also, let's make this stereo. Okay, so let's run this. This takes a bit more. Okay, as you can see, things are starting to get a bit more interesting. But we don't have damping yet, so this is still ringing forever. So let's add some damping to obtain something more interesting. So the first thing we notice is that we have another parameter, which is damping coefficient. We can now simply take this value, 0 equals 500. Well, now we have to redefine our coefficients. So first, let's set the neighborhood radius, which is still 1, and time coefficient, which is still 1. But then for our points, we will have a equals this. And then we'll have b equals lambda squared over c1, which is this. And then c will be c2 over c1, which is this. And then let's define what these two things are. C1 equals then C2 is going to be the same with the sign inversion. As before, we can write mid coef equals b a b, and mid coef the equals 0 c 0. We're not gonna implement any other boundary conditions. We can simply call our scheme function, well, declare. Now we can simply, we will simply have a par iteration, par, no, sorry, points min coef del. We can keep this structure as before, and let's try and run this. Yeah, of course, he is complaining because here I miswrote this. Let's run this. And okay, here we have it. Let's try. This starts to be a bit more interesting. At least it sounds more like a string. We can decide where to excite it. And so as you can see, by using the library, it's way easier to write fine difference schemes in Faust. Before concluding this tutorial, I would like to briefly show you something more advanced. So until now, to excite our model, we used an impulse directly sent through the mesh. And here I'm still on the damped wave equation code with only 5 points. Now, in reality, things are of course more complicated, and interaction is usually nonlinear, and it depends on the current state of the mesh or of the model. This is called coupling, and now I'm going to show you how to implement this in Faust with an example. I had to reduce the zoom because of a GUI problem, but you can go to examples, physical modeling, FDS, piano hammer string. Okay, so let me reduce the number of points for more clarity. I'm gonna run. And this is our new process diagram. So as you can see, instead of having only one sequence of functions as before, here we are taking the value of each point, feeding it back. And here we use an interpolation function to get only one of these signals, the one we are interested in, and to drive it inside the hammer function. This takes in the position of the point or the state of the point of the string that we want and outputs a force. And then we use another interpolation function to drive it to the string points exactly as we were doing before. Here then, to get only one signal from one point out, we interpolate out exactly like we were doing before. And let me just show you the process function for this example. This is just one big feedback loop. It's what's inside here. So one interpolation function, the hammer function, which is inside the FD library. Another interpolation function, the model, then a bus, and interpolating out. So just to let you hear how this sounds, let me increase again the number of points. Takes a while, of course. And as you can see, this is a bit more interesting than before. Okay, this is the end of the workshop, and first of all I would like to thank you all for your attention. And since time was limited, I had to rush on some topics, so if you have questions or if you want to deepen some of the things I talk about, you can reach me at this email address. And yeah, bye.